On August 17, 2025, the third interstellar object ever confirmed to enter our solar system passed its closest point to the Sun. It had been traveling at 153,000 miles per hour. It had arrived from another star system, older than our solar system by possibly billions of years. And in the weeks surrounding that perihelion passage, it did something that left the scientific community scrambling for an explanation. It lost mass at a rate that was mathematically impossible for the object scientists thought they were looking at. The numbers don't lie, and they didn't match. And the attempt to reconcile what the telescopes showed before perihelion with what happened after perihelion produced one of the most genuinely baffling scientific puzzles the study of interstellar objects has produced in the 8 years since the first one was ever detected. This is what actually happened to 3I Atlas, and nothing about it is simple. 3I Atlas was discovered on July 1st, 2025, by the Atlas Survey Telescope in Rio, Hurtado, Chile. The same telescope network that lent it its name, its orbital parameters confirmed immediately what the discovery team already suspected. This was not a solar system object. The eccentricity was 6.145. A gravitationally bound orbit has an eccentricity below 1. An object with an eccentricity of 6.145 is not just unbound. It is traveling at a speed so far above solar escape velocity that no process inside our solar system could have produced it. 3I Atlas came from somewhere else. It arrived at approximately 137,000 miles per hour when first detected, already inside the orbit of Jupiter, and it was decelerating as the Sun's gravity tried and failed to capture it. It joined a list of exactly 2 other confirmed interstellar objects. 1MINUTE, detected in 2017, which was elongated, showed no outgassing, and accelerated in ways that solar radiation pressure alone could not explain. And 2I Borisov, detected in 2019, which behaved like a perfectly normal comet in almost every respect, outgassed predictably, fragmented slightly after perihelion, and left the solar system without particular mystery. 3 interstellar objects detected in 8 years, and where there were once assumed to be almost none, there are apparently many. The galaxy may be full of them. 3I Atlas occupied a strange middle ground between its 2 predecessors. It was unmistakably cometary. It had an icy nucleus. It had a coma, the bright cloud of gas and dust that surrounds an active comet as it warms. By early August 2025, when NASA's Sphere-X instrument captured detailed spectral observations, the coma's carbon dioxide envelope extended 348,000 kilometers from the nucleus, roughly the distance from Earth to the Moon. A vast cloud of gas erupting from something that, at that point, had barely entered the inner solar system and was still millions of miles from its closest approach to the Sun. The nucleus was the problem. Hubble Space Telescope observations taken in July 2025, 3 weeks after discovery, constrained the diameter of 3I Atlas's nucleus to between approximately 440 meters and 5.6 kilometers. That is the uncertainty range. The true diameter sits somewhere inside those bounds. Based on the brightness data, the best estimates clustered toward the lower end of that range, a nucleus perhaps 1 to 2 kilometers across. Then the object approached the Sun, and the mass loss began. When Webb observed 3I Atlas on August 6, 2025, still weeks before perihelion, the object was shedding approximately 150 kilograms of material per second. That is a substantial outgassing rate for a comet. It is not unusual for an active comet approaching the inner solar system. It is a number that makes physical sense given what the Hubble data suggested about the object's size. When the Webb data was taken on August 6, 2025, 3I Atlas lost only 150 kilograms per second. The mass loss at perihelion derived was 4 orders of magnitude larger, about 2 million kilograms per second. 4 orders of magnitude. That is a 6,000-fold increase in mass loss rate between early August and perihelion on October 29th, from 150 kilograms per second to 2 million kilograms per second. Daily mass loss at peak reached figures that strained belief, and the energy budget behind that mass loss is where the mathematics became uncomfortable. In order to sublimate sufficient carbon dioxide and water ice to match observed mass loss, the absorbing surface area of 3I Atlas would need to have been larger than 617 square miles, equivalent to a sphere with a diameter of 14.3 miles. 14.3 miles across. The Hubble data had capped the nucleus at 5.6 kilometers, roughly 3.5 miles, at the absolute upper end of uncertainty. The minimum surface area required by the energy calculations was 16 times larger than the maximum nucleus size the imaging data allowed. You cannot hide a 14-mile object from Hubble's optics. The discrepancy was not measurement error. The numbers were simply not compatible with each other under the assumption of a single intact nucleus. Harvard astronomer Avi Loeb, who has written extensively about interstellar objects since the discovery of 1MINUTE, laid out the arithmetic publicly. Breakup into fragments would have increased the surface area of its material. Since the surface-to-mass ratio scales inversely with the characteristic radius of fragments, an increase in surface area by a minimum factor of 16 requires that 3I Atlas broke into at least 16 equal pieces, and likely many more. This would mean that 3I Atlas exploded at perihelion, and we are witnessing the resulting fireworks. The fragmentation hypothesis is the most natural explanation for the numbers. If the nucleus shattered under the thermal and tidal stresses of perihelion passage, the combined surface area of millions of smaller fragments would add up to the absorbing area the energy calculations demand. The problem of reconciling a small nucleus with an enormous mass loss rate dissolves if the nucleus is no longer a single object. It is a cloud. The post-perihelion imagery seemed at first glance to support this picture. On November 8, 2025, astronomers observed 3I Atlas at 29 degrees separation from the Sun. Their stacked images showed a large glowing halo extending to 500,000 kilometers with at least 7 distinct jets, some of which were anti-tails in the sunward direction. 7 distinct jets, not a single tail blown back by solar wind, the standard appearance of a comet after perihelion. A complex, multi-directional jet structure, including anti-tails pointing toward the Sun rather than away from it, stretching to nearly 1 million kilometers in the sunward direction and 2.85 million kilometers in the opposite direction. The outermost mass density of the jet gives a mass flux of 2 million kilograms per second per million kilometers squared, summing over an area of order 10 million. Kilometers squared yields a mass loss rate of 50 billion tons per month. 50 billion tons per month, sustained after perihelion. The jets were not fading, they were organized. Complex directional structures extending across distances approaching the Earth-Sun separation, clearly resolved across multiple independent observations from different telescopes on different continents. What caused those jets? Thermal stress from solar heating is the standard answer for cometary activity. Rotation-induced outgassing, volatile ices sublimating as different faces of the nucleus are exposed to sunlight, can produce jet structures in comets. And 3I Atlas had arrived from interstellar space, having potentially never been this warm in billions of years. The surface layers and subsurface volatile deposits would be responding to solar heating for the first time in an incomprehensibly long period. There was no reason to assume its perihelion behavior would match that of a solar system comet that has completed dozens of orbits and had its most volatile surface material long since depleted. The scientific community's formal assessment, however, was more cautious than the dramatic numbers initially suggested. Spacecraft observations confirmed there was no substantial splitting of the 3I Atlas nucleus or other unusual behavior during its perihelion period. The monitoring data from multiple spacecraft tracking the object through perihelion showed no clearly identified fragments branching off the main body. The post-perihelion jets, as dramatic as they appeared in ground-based stacked imaging, were consistent with intense cometary outgassing from a nucleus that had survived intact but was losing material at extraordinary rates as newly exposed subsurface volatiles responded to solar heating for the first time. The picture that emerged was not clean fragmentation and not intact normal comet behavior. It was something in between, and something that the existing models for cometary perihelion passages had not anticipated at this scale. Researchers described the phenomenon as beyond standard. Cometary models, highlighting the challenge of explaining its behavior using existing theories. SphereX reobserved 3I Atlas in December 2025 after perihelion and found increased activity compared to the pre-perihelion baseline, along with refractory coma dust and new coma gas species that had not been detected in the earlier observations. The post-perihelion object was chemically more complex than the inbound one. Whatever happened near the Sun had exposed material that was not visible before. The broader context for 3I Atlas places it in a category that current planetary science has no established framework for. Kinematic analysis of its pre-encounter trajectory suggests 3I Atlas is likely an object from the galactic thick disk, a remnant of the galaxy's cosmic noon period of intense star formation, approximately 9 to 13 billion years ago. If that classification holds, the object that just passed through our inner solar system ejecting 2 million kilograms per second of material near perihelion was formed when the Milky Way was young, in the first few billion years of the galaxy's existence, around stars that have long since burned out and died. It has been drifting through interstellar space for potentially longer than our solar system has existed. That age matters for what happened at perihelion. A 9 billion-year-old cometary object arriving at solar heating for effectively the first time would have subsurface volatile deposits largely undisturbed. When those deposits reached sublimation temperatures, the response would not be gradual and predictable in the way a returning solar system comet's response would be. It would Be sudden, intense, and potentially catastrophic in terms of mass loss, as the thermal wave reached volatile layers that had been locked at near absolute zero temperatures since before the Earth formed. 3I Atlas's eccentricity of 6.15 and hyperbolic excess velocity of approximately 58 kilometers per second are even more extreme than those of both Oumuamua and Borisov, making it the most dynamically extreme object of the 3 confirmed interstellar visitors and suggesting it may be the oldest sample from the Milky Way thick disk yet studied. What 3I Atlas leaves behind, as it now heads back out of the solar system toward Jupiter's orbit and beyond, is a dataset that planetary scientists will be working through for years. The mass loss paradox has not been fully resolved. The energy calculations still require either a nucleus that was larger than Hubble allowed, or the fragmentation on a scale that the spacecraft monitoring did not directly confirm, or some combination of the two that current models do not yet capture. The post-perihelion jet structure was real, documented across multiple independent observatories, and consistent with something more intense than standard cometary outgassing models had predicted. The standard model for what a comet does when it approaches the sun was built on decades of observations of solar system. Comets, objects that formed in our own protoplanetary disk, objects that have been on elliptical orbits cycling through the inner solar system across millions of years. 3I Atlas was none of those things. It formed around a different star in a different era of the galaxy's history. It had never been this close to any star, and the physics of a first-time solar encounter for a 9-billion-year-old interstellar object, arriving with a velocity 58 kilometers per second beyond solar escape velocity, appears to be physics that the existing models did not fully anticipate. That is not a failure of science. That is science working exactly as it is supposed to. An object arrived from outside the solar system, and it behaved in ways our models did not predict. The models now have to update, and the next interstellar object, whenever it arrives, will be studied with the knowledge of what 3I Atlas did, and the instruments will be better aimed. 3 interstellar objects in 8 years. The galaxy is not empty between the stars.